Hello everybody, my name is Diego Gomez and today I'm going to present the precision measurement of cosmic ray deuterons with the Alpha Magnetic Spectrometer on behalf of the AMS collaboration. The AMS experiment is a high-precision particle detector on board of the International Space Station since 2011, and it has recorded more than 180 billion cosmic rays. Cosmic ray primary nuclei are produced in supernova explosions and accelerated in supernova remnants. These primary nuclei travel across the galaxy and interact with the interstellar medium, producing secondary particles. Among those secondary particles are deuterons, produced by the fragmentation of helium nuclei with the interstellar medium. For this reason, cosmic ray deuterons are important to understand the amount and the characteristics of matter crossed by cosmic rays in their travel through the galaxy. Because of the longer interaction mean-free path of deuterons compared to heavier secondary nuclei, they contribute to a more complete description of the propagation process, helping to set new constraints in propagation models. Additionally, deuterons are the most abundant secondary species in the galaxy. These are important motivations to measure the deuteron flux and the deuteron-to-helium-4 ratio. For more information about the helium and lithium isotopes and the new properties of secondary cosmic rays, please see these other AMS talks. The AMS detector is composed of different subdetectors with different physical principles. It has a transition radiation detector to measure electrons and positrons, a silicon tracker detector to measure the absolute value of the charge, and the trajectory of the particles deflected by the magnetic field. With this information, the rigidity defined as the momentum over the charge can be calculated. It also has an electronic calorimeter at the bottom of the detector to measure the energy of electrons and positrons. AMS also has a time-of-flight detector to measure the charge and velocity of cosmic rays. The charge sign is determined by the direction of the curvature produced by the magnetic field. Additionally, AMS has a ring imaging Cherenkov detector to measure the charge and velocity of isotopes. In AMS, a deuteron is identified by its mass. From this equation, we can observe that in order to calculate the mass, we need the charge, rigidity, and velocity of the particle. The charge is obtained from three different detectors: the time of flight, the layer 1 of the silicon tracker, and the inner silicon tracker. These three independent measurements give an excellent charge reconstruction and avoid charge confusion. Only particles with charge 1 were selected. The rigidity is measured with the inner tracker through the reconstruction of the particle's trajectory and the intensity of the magnetic field. Only cosmic rays with good track were selected. The last component is the velocity. This is obtained from two different detectors, the time of flight and the ring imaging Cherenkov detector. I will show in more detail this measurement in next slide. The velocity in the time of flight detector is calculated from the time difference it takes to the particle to go from the upper to the lower plane of the detector. The resolution for charge 1 particles is about 4%. The physical principle to get the velocity from the ridge detector is different. A particle interacting with the radiation material produces a Cherenkov light cone with an opening angle from which the velocity is obtained. This angle in the cone is reconstructed from the matrix of photomultipliers on the bottom of the detector and from the trajectory of the particle. The ridge detector has two types of radiators, sodium fluoride and aerogel, each one with a different refractive index. As a consequence, the velocity can be measured in two complementary regions, above 0.75 for sodium fluoride and above 0.96 for aerogel. The resolution for charge 1 particles is about 0.35% for sodium fluoride and 0.12% for aerogel. Since the identification of deuteron is based on the calculation of their masses, it is important to understand the performance of the detector to measure the deuteron mass. The mass resolution depends on the rigidity resolution and the velocity resolution. This is why the mass resolution is obtained in three energy regions, defined by the time of flight, the sodium fluoride part of the ridge, and the aerogel part of the ridge, as shown in the figure. We can observe deuterons can be separated up to 10 gigaelectronvolts per nucleon. However, an event-by-event identification is not possible. Therefore, deuterons have to be extracted from the shape in mass distribution using template fits in beta slices. In this slide, we can observe an example of the template mass fit in different beta bins for the three different energy regions, time of flight, sodium fluoride, and aerogel. In the three figures, the black dots represent the mass distribution measured by the detector. The color lines are templates obtained from Monte Carlo simulations that reproduce all the effects in the detector. The red line represents the pronounced proton peak, and the blue line represents the deuteron peak in every one of the figures. The green line is the background from particles with charge 2 that fragmented into charge 1 particles above a layer 1. This background represents less than 5% of the deuterons. The magenta line represents the addition of the three different templates, and it fits well the data mass distribution. From the deuteron template fit, we can obtain the number of deuterons as a function of energy and to calculate the flux. Here I'm presenting the latest results for the deuteron flux as a function of rigidity. The flux goes from 2 gigavolts up to 20 gigavolts, and it includes systematic and statistical errors. In this plot, I am presenting the latest result for the deuteron flux as a function of kinetic energy. This flux is compared to other measurements made by previous experiments. As you can see, the deuteron flux measured by AMS reached a higher energy up to 10 gigaelectronvolts per nucleon, and it has a higher precision. Another result of this analysis is the deuteron-to-proton ratio as a function of rigidity. As you can observe, the deuteron-to-proton ratio has a small increase from 2 gigavolts up to 7 gigavolts, and then it reached a constant value. Finally, I'm presenting here the results for the deuteron to helium-4 ratio as a function of rigidity. As you can see, The deuteron to helium-4 ratio is more or less constant at low rigidity, and it starts decreasing at high rigidity. In conclusion, a deuteron flux measurement is important to bring light into a complete description of the cosmic ray propagation process in the galaxy. For this reason, a deuteron flux was calculated using more than 15 million events collected by AMS from May 2011 to January 2020. This flux was measured as a function of rigidity from 2 gigavolts up to 20 gigavolts, and as a function of kinetic energy per nucleon from 0.2 up to 10 gigaelectronvolts per nucleon. The deuteron flux measured with AMS has reached a higher energy and a higher precision than previous measurements. Additionally, the deuteron-to-proton ratio and the deuteron to helium-4 ratio were also measured as a function of rigidity. Thank you for watching this presentation.